All right, let's go ahead and take a look at some of the information necessary to complete the module folder 3A pre-lab for densities. This one, like most of our other ones, will have a simulation that goes along with it. I've gone ahead and preloaded that just in case there were any issues. Sometimes it's a little bit slow. So before we get started, we do need to change a couple of settings. We need to make sure to pick the right section because there are some options here. So according to the instructions, we're going to use the compare option. Okay, so we're going to click to move into here. Then in order to be a little bit more consistent, we do want to click and see same volume. Okay, so otherwise, we have the same mass on each of these, right? You can see they're each 5 kilograms, but we want to show same volume, right? So the same size, but they've got different masses now. And then this volume can be scaled up or down. So let's see what we want to do. We want to use 10 liters, right? So that's in the instructions as well. So maximum volume. Notice then these are all exactly the same size as each other. We can put them all next to each other. I may have to hold the last one. Oh, no, it'll stay. And see they're all the same size as each other, but they're marked with different masses. That's going to change how they float. So let's see if I can put them in order. So they're all the same size. The different mass means that they basically try to push down harder into the water. Then when that water is displaced, it pushes back, giving a buoyant force. And that buoyant force will be different, and therefore the volume will be different depending on the mass and eventually the weight that it's supporting. Okay, so let's see how we can use this to find anything. So let's clean up our mess. Because it'll all fit over here, let's go ahead and just do that. Okay, so we want to take the 2 kilogram block, put it in the water by itself, determine the change in the water level. So if we look, water is 100 liters. Bring this over. So notice that 2 kilograms made this go up to 102 liters. The difference between 100 and 102, I think is fairly obvious. That's 2. Okay, so there we go. That was easy. Then we want to do the same thing with 4 kilograms. So we'll take this one, we'll put it back, grab out the 4. Notice that even if I drop it, or if I hold it under, that it will eventually balance back out. So, okay, so 4 kilograms means here 4 liters. Okay, then look, 6 and 8. So let's go ahead and try 6 and 8. Stack this one over here out of the way because we're done with it for now. Oh, simulation's acting up. All right, there we go. So 6, as we might have predicted, gives a volume difference of 6, and 8 is a volume difference of 8. I'm not sure how I managed to make that one float, but whatever. Okay, so 6 liters and 8 liters. And if we'd had a 10, then I think you could guess what that would do. So what, if anything, seems to be true about all of the previous answers? So, we had 8 kilograms and 8 liters, 6 kilograms and 6 liters, and so on. And so it seems to be that the displacement matches the mass of the block, right? Can we think of any reason that might be true? So, let's work into that and let's see what's happening, all right? So let's try this now with the 8 kilogram block. What we want to keep in mind here, and again, this is sort of foreshadowing for a future question, the block is set to have a volume of 10 liters. What we've measured over here is the change in water, the level, so the amount of water that's been displaced. So be careful not to misconnect these pieces of information. So if we divide the mass of the block by the amount of water displaced, right? So if we take 8 divided by 8, then we get 1. And then because we're doing mass divided by volume, kilograms divided by liters, technically that could help you to narrow this down in the first place. Now, this is the tricky part, and like I said, where you need to be careful not to misconnect some information. The information here, the volume of the water is 8 liters. The volume of the block is 10 liters, right? So those are different numbers, but the mass of the block and the mass of the water is the same. That's what allows these to balance out and to float. Technically, what's balancing is the force. So this block mass times gravity is equal to the weight of the water being displaced. And then those forces balance each other, and this can sit. So 8 kilograms of water is displaced. 8 liters of water is displaced. 8 divided by 8 is 1. And water is expected to have 1 kilogram per liter density. So it turns out that's actually the density of the water. Okay, so in the next question, we want to do the same thing. So we're looking at the same block in water. But this time, when we're given the step to find a density, we're going to divide the mass of the block, which was, again, 8 kilograms, by the set value for the volume of the block. So remembering that the actual full entire block itself is 10 liters, then we'd have 8 kilograms here. We're not going to look at the water level this time, but we're going to look at the 10 liters set on the side. So 8 divided by 10. Same as 4 over 5 if you decide to make a fraction, or 0.8 if you decide to use a decimal. This one should make sense though. Any of these numbers that are either 1 or greater are not going to float on top of the surface. So if I pull this underwater, if it was more dense than water, it would stay there. However, we can see it floats back up. If it was exactly the same density, then it would just stay wherever I put it. It would suspend, but it wants to float. So the only density that was less than the water density was 0.8, so that's what it had to be. Okay, so now that we've used the actual block volume here, that means the answer that I found that time is actually the density of this block. Again, you want to remember that the blocks floated differently. So if I take, say, this 6 and put it next to this 8, they have different masses, but they have the same volume. So that means that they're going to end up with different densities. You can also see that they float different ways. So it's just the density of the one block. Okay, and then last question here. We can connect these as long as these are uniform shapes. It's kind of easy to see what's going on. But roughly 4/5 of this block is underwater, which conveniently is the same ratio as 8 over 10 if we were to set these and reduce to 4 over 5. As it turns out, the amount of the block that's underwater tells you its density, or how its density compares to water, and we can call that specific gravity. So notice that each of these, as they go lighter, has a smaller and smaller portion of the block that's underwater. It's like this red one is 1/5 underwater because 2 is 1/5 of the volume. The one we're looking at here, 8 kilograms, 8 over 10 would be 4 over 5. So be careful to select the choice properly. 2 of these say 4 over 5, but this says 4/5 of the block is above the water. And that wasn't true for this one. That was true for the red one. That's the 2 kilograms. But this, I guess that's sort of a darkish yellow. But this yellow one is the one that we're trying to look at. And there we go.